All right. So, very much like the questions we have been doing off the worksheets. Okay? And also, very much like what you will see on your unit exam in terms of work energy theorem questions. So, if you felt you didn't know how to do this, pay attention very closely today. Okay? All right. We always say the first step is write down your givens. The second step is probably even more important than that, is identify what type of energy is being changed. In number 1, what kind of energy is being changed? Kinetic, the speed is increasing. In number 2, potential, the height is changing. All right. So for question number 1, give them a mark for their givens. Mass was 200 kilograms. Initial velocity or initial speed was 2 meters per second. Final speed was 8 meters per second. And the distance over which it happened was 13 meters. Okay. Second mark if they wrote down work energy theorem. So if they have work as a change in energy, or they went force times distance equals mvf squared minus 1/2 mvi squared, if there's something along those lines that looks like work energy theorem, give them a mark. Okay. Now, if I want to find the force that is used to accelerate this object, okay, this cart, right, I need to get rid of d. So how do I move d over to the other side? Just divide by it, right? Okay, so I divide both sides by d, I should end up with this. Okay, so if they have this, right, give them a mark for that. That's the properly manipulated version of this. You can give them another mark if they plugged in their numbers correctly. 1/2 times 200 times 8 squared minus 1/2 times 200 times 2 squared. Okay, that divided by 13 meters should give us 461.5 newtons. Make sure the units are right. Okay, it does need to be in newtons as its force. Okay, not joules. All right, so that one is out of 5. Okay, any questions on that one? All right, we said in number 2, the potential energy was what was changing. All right, we know that because the height is changing. So give them a mark first. Okay, for their givens, 65 kilograms, initial height 13 meters, and the work that's done, in other words, the change in energy, is 450 joules. Okay, again, a mark for work energy theorem. Work's a change in, this time, potential energy. Okay, and we're looking at then mghf minus mghi. Now, I haven't put in force times distance for work here. Why? I already have it. They gave it to me in the question. There's no sense putting in FD. I already know what FD equals. It's 450 joules. All right. Now, I want to get the final height, this term here, by itself. Now, rules of algebra say, okay, that if you want to move something, you should do the opposite. And what should you move first? Things not attached. That's that half rule, and it applies here. MGHI is not attached to HF. Therefore, I should move it first. So I'm going to add it to both sides. So I'll have work plus MGHI equals MGHF. Then, they're all being multiplied together. They're attached now. I can divide both sides by MG, and that will leave HF by itself. Note here, MG and MG do not cancel. Okay, this has to be done before that. Okay, everybody with me there? All right, so give them a mark if they had the manipulation as well. A mark for plugging in the numbers. 450 joules plus 65 times 9.81 times 13, okay, divided by 65 times 9.81. Okay, give them a mark for that. And our final answer should be 13.7 meters. So they didn't move it very far. Okay, only 0.7 meters. Okay. All right, that one is also out of 5. Questions on that one? Peter. Did they do the delta H thing? I'll come and have a look. All right. So what we're going to go over today, guys, is conservation of energy. Okay. So conservation of mechanical energy. We introduced this a little bit yesterday when we were talking about one of the work energy theorem problems where the guy had jumped out of the plane. Okay, and we calculated his potential energy when he was jumping out of the plane, and we had found that it was equal to his kinetic energy when he hit the ground. Okay, does everyone recall that? Right? The reason that is because the plane has done all this work to get that person up to whatever altitude he jumped from. Okay? That's the amount of energy that's going to be with that person until they do work on something else. Okay? That's what the law of conservation of energy says. Barring any input or output of work, the mechanical energy of an object or a system remains the same. Okay? Everyone follow me there? Which sort of makes sense. If work's a change in energy and you don't do any, you have to keep all the energy you have. Agreed? And now, again, that's in the perfect physical world. Okay? Obviously, at all times, we're kind of bleeding energy away. Okay? That's why this room, I don't have to turn the heat on in this room. I just let you guys heat it up. Okay? That's why it's always cold when you come in. Okay? But by the end of the day, it's nice in here. Okay? Because every time there's 30 people in this classroom, it gets warmer. Okay? We're all bleeding energy away in the form of heat, okay, from our bodies. We're not conserving it, we're transferring it away as heat. Okay? We're kind of doing that. We're not doing work, we're doing heat. I know that doesn't sound right, but that's what we're doing. Okay? The transfer of thermal energy away. All right? Question? Right. You can't change how much energy exists. You can change what form it's in, but you cannot change the amount of it. Okay? All right, so first off, we're going to review quickly what is mechanical energy. Okay, mechanical energy is the sum total of kinetic and potential energy of an object or system. Okay, now we've looked at this example I don't know how many times, but we do because it's perfect. Okay, the bow and arrow example is a perfect example, okay, of a system. Right? The system in the bow and arrow here is the person, the bow, and the arrow. Okay? Those are all the parts of the system. Okay? The energy may be shared by all of those parts, or it may be possessed by only one part at any given time. Everybody with me there? Okay. Right now, what part of this system has all the energy? Yeah, the bow does. Okay? Because the person has done work already. They've drawn back the bow. They've exerted a force through a distance. Now the bow has elastic potential energy. Okay? When they release the bow, in the process of the bow snapping back to its original position, what part or parts of the system will have the energy then? The arrow. And the bow, in the process of snapping back, right? So the bow, that means while the bow is pushing on the arrow, the bow is transferring energy to the arrow. They both have some during that energy transfer. Okay? And then when the arrow leaves the bow, then only the arrow has all the energy. Okay? It's being converted from different forms though. Okay? Initially it's chemical energy within this person's body. Okay? Then it becomes mechanical energy within their muscles. Then it becomes elastic potential energy within the bow, and then it becomes mechanical energy within both the bow and the arrow, and then finally kinetic energy within the arrow. Right? But the amount of it is always the same. If that person does 1,000 joules worth of work, that's all the energy that system will ever have. Everyone's good with that? Okay. Now, is this calculation here a pretty easy calculation? Yeah, I mean, especially when it's written like this, okay, EK plus EP. Now, in reality, this might be a little more involved than just adding two numbers together, because realistically, mechanical energy is really 1/2 mv squared plus mgh, okay, because those are the formulas for EK and EP, and that's how we're going to do that most often. All right, now, first example problem here. We got a 300-kilogram baseball, and it's thrown in a straight line through the air. Okay? At a height of 2.50 meters above the surface of the Earth, it has a speed of 20 meters per second. Does this baseball have mechanical energy? It does, because it has height, which means it has potential, and it has speed, which means it has kinetic. It is possible for an object to have both. Okay? In terms of mechanical energy, it is possible, and in fact, it is not just possible, it is quite common, okay, for an object to have both kinds, okay, of energy, kinetic and potential. Right? Which is why, rather than looking at them as separate entities, we use mechanical energy to describe the total energy of the object. Okay? All right, so if I want to find the total mechanical energy of the baseball, okay, I start out with this. Mechanical energy is potential plus kinetic. Okay, plug in those formulas and plug in my numbers. So 1/2 times the mass of the baseball times the speed of the baseball squared. Add that to mass of the baseball times acceleration due to gravity times the height of the baseball. Right? Now I have the potential and the kinetic energy of the baseball. When I add those together, I have 60 joules plus 7.36 joules, and that gives me 67.4 joules. Okay. Everybody all right with that? Okay. Is that a pretty simple calculation? Yeah. What if the question instead asked me to calculate the kinetic energy and gave me mechanical and potential? Would I be able to do that? Okay, I would just do what with EP? Subtract it over to the other side. Okay, and you're going to be asked to do a little bit of that as well. All right. All right, so the example here we've already talked about. Okay, the bow and arrow there, right? Important concept in physics that involves mechanical energy. Person pulls the bowstring. Okay, they're doing work. Okay, work stored in the bow is EP elas, they call it. Okay, elastic potential energy. Right, when the string is released, the elastic is converted to kinetic. Okay, the arrow is released. All right, everyone follow me there. Everyone's good with that explanation, right? Good, because there's almost always some version of a bow and arrow on your unit exam. Okay, in the past few years it's been bow and arrow, slingshot, catapult. I mean, they all have the same thing in common, right? You change their shape so they have elastic potential energy and you convert it into something else, okay, by doing work. All right. Okay, I want you guys to try 8, 9, and 10. And I will put the answers up there, okay, so you can check and see if you've done them right. Okay, just going to quickly run through number 1 here. I know you guys have probably all got it done already. Okay, so mechanical energy is potential plus kinetic. All right, so that's going to mean mgh plus 1/2 mv squared. Okay, and we just plug in our numbers. 0.3 times 9.81 times 30. Okay, plus 1/2 times 0.3 times 8. Yeah. Times 8 squared, right? And that should give us our 97.89 joules. Okay, that's about as easy as they come. How are we doing on number 9? How many people have done number 9? Okay, let's go over that one too then. All right, so on number 9, we're trying to find the potential energy, okay, of this high jumper here. All right, so for that, okay, we start out with this. EM equals EP plus EK. I'm trying to find EP, so what do I do with EK? Subtract it. All right, so EP is going to equal mechanical energy minus kinetic energy. All right, so that's going to mean they told us that they had 3,000 joules worth of energy. Okay, worth of mechanical energy. We got to subtract the kinetic from that, so subtract 1/2 times 55 times 8.33 squared. Okay, and when we do that, okay, we should get 1,091.8. Yeah, 0.8 joules. All right, now extension from this. What if the question asked me to calculate how high above the ground they are? Would I be able to do that? Yeah, I just figured out what m times g times h equals. Agreed? Right, because that's the potential energy. Okay, so if this number, okay, equals m times g times h, and I know both of these, right? They told me he's a 55 kilogram athlete. G is always 9.81. I can easily solve for how high this person had jumped. Okay, so 1,091 divided by 55 times 9.81 will give me 2.02 meters, which, take it from me as a high school track coach, is an impressive high jump. Okay, because 2 meters is this much taller than me. Okay, yeah, so that's pretty impressive, right, for someone to be able to high jump over me by that much further. I definitely wouldn't stand there because I have no confidence in that. But okay, it's pretty high. If someone's jumping over 2 meters, they're flying, right? And guys at the Olympics are, you know, close to 3. Okay, sometimes more than 3, right? Which is sick. Okay, to watch. If you ever watch somebody do high jump who's really good at it, it is incredibly cool to watch. They're just like a noodle. And they bend really weird as they go over. Okay. All right. How many people are done number 10? How many people are stuck on 10? Okay, let's go over number 10 then. Okay, so for number 10, we got the construction worker dropping the hammer from 50 meters above the ground. Okay, so we're trying to find the kinetic energy of the hammer. So we start out with EM equals, okay, EP plus EK. Now we're trying to find EK. It's pretty much the same thing we did up here, except that we don't subtract EK, we subtract EP. All right, so EK, the kinetic energy, is going to equal the mechanical energy minus the potential energy. Now they tell us that the mechanical energy is 1,880 joules. Okay, and we have to subtract M times G times H from that. Okay, so that's going to be 1,880 minus 2 kilograms times 9.81 times 50 meters. Everybody with me there? Right? When we do that, we should get 899 joules. Okay? Now, extension from this. Could I find out how fast the hammer is going? Sure I can. I just calculated the kinetic energy. If I know the kinetic energy, I should be able to find V, because I know this number equals 1/2 mv squared. All right? So if I want to find V, I divide both sides by half of m, so that's 1/2 times 2, okay, and then I take the square root of that. So 800, I'm looking for the square root of 899, because dividing 899 by half of 2 is dividing by 1. And that doesn't change the number, right? Okay, so the square root of approximately 900, okay, is just about 30, right? So yeah, it's 29.98 or something like that, so it rounds to 30 meters per second. So that's kind of where we're headed. Okay, we're not quite there yet, but that's where we're headed. Okay, they would give you information about a point, okay, and you would have to calculate speed or height of the object. Okay, questions so far? All right. Okay, now this is work-energy theorem combined, okay, with law of conservation of energy. If I use a force of 100 newtons and pull back a bowstring 1/2 meter, how much work have I done? Not 50 newtons. 50 joules, right, okay, because work is in joules. All right, so how much work is done on the bow? 50 joules, because it's force times distance. 100 newtons, okay, times 0.5 meters is 50. All right, now, how much potential energy is in the bow? 50 joules. That requires no calculation, because the bow and arrow system can only have as much energy in it as you've put into it by doing work. All right, that is why every single answer is 50 joules. Agreed? We talked about this right at the beginning, right? Okay, so how much kinetic energy does the bow have? 50 joules. Okay, or sorry, does the arrow have? Okay, how much potential energy will it have at its highest point? 50 joules. Okay, none of that ever changes. Now, if I knew the mass of the arrow, would I also be able to calculate its speed leaving the arrow and its maximum height? Yeah, because I know the energy. Okay, and those are the kind of things you're going to be asked to do. All right. Oh, there they were. I knew I had them written down somewhere. Oh well. All right. Law of conservation of energy. Law of conservation of energy in words says that energy can't be created, it can't be destroyed. It says that as long as you've put work into a system, that energy will always be there. Mathematically, that's written like this. The initial mechanical energy of an object or system is equal to the final mechanical energy of the object or system. Agreed? If I can't create it and I can't destroy it, then it must always be the same. And that means that the mechanical energy of an object at any 2 points is the same. Does that mean the kinetic and the potential are the same? No, it doesn't. They could be different, but they're always going to add up to the same number. If, for example, you're riding a roller coaster, and this is a very simplified roller coaster, because that's all I can draw, right? I got the cart up here, and the cart, let's say, here. So down here, the height is 0. Up here, the height is, let's say, 40 meters. Okay? Where's the cart going to be going fastest? At the bottom, because down here, all of its mechanical energy will be in what form? Kinetic, because it can't have any potential. Its height is 0. Now up here, it's probably going to be moving pretty slow. And it's going to have some kinetic energy, but most of its mechanical energy will be potential. Right? And then as it goes down the hill, the potential will turn into kinetic, same as the skydiver yesterday. Right? The mechanical energy, though, isn't going to change, because the mechanical energy is always the sum of these two things. And since they're always turning into each other, they always add up to the same number. Is that all right with everybody? Okay. All right, so that's what the law of conservation of energy basically just says. The total amount of energy always stays constant. Okay? And it can be converted from one form to another. We simplify it a little bit and we say it's always going to be from potential to kinetic and kinetic to potential. We're going to ignore the fact that in the real world it's turned into sound, heat, light, whatever else. Okay? Because obviously those are what we call non-conserved forces. Okay? They're forces against friction, okay, and stuff like that. And they represent energy that gets lost. Okay? It's not destroyed, it's just turned into things that don't do work anymore. Everyone follow me there? All right, so we're going to simplify it. We're only going to pretend that these are the only forms of energy, and that makes life easier. Okay. All right, now, if I'm dealing with, let's say, this spot up here, and the cart's not moving, and this spot down here where the cart is moving, the potential energy here should equal the kinetic there. Okay, that's what we're saying here. EI equals EF. If it's got no kinetic energy up here, all of its energy is potential. Okay? Very rarely do you run into a conservation of energy problem that simple. Okay? Most of the time, you're going to have potential and kinetic at both points, like you would, let's say, if you were here. Okay? Let's say you're here and you're 20 meters off the ground. Do you have both kinetic and potential there? Yeah. All right, so let's look at this example here. A rock is dropped over the edge of a cliff, a 30-meter high cliff. Okay? What's the speed of the rock just before it strikes the surface of the lake? All right. Any forces other than gravity here? All right. If there's no forces other than gravity, then we can assume that this is the perfect physical world. EI equals EF. Okay. Potential is going to be turned into kinetic and vice versa. All right. So I can apply this. EI equals EF. What kind of energy does it have when I'm about to drop it? Potential only, right? It's not moving, only has potential energy. So I can say then, okay, I should really write it like this, because this is what we mean. This is mechanical, and this is mechanical. So what we're really saying is that the initial potential plus the initial kinetic equals the final potential plus the final kinetic, right? That's what we're saying. If mechanical energy equals the sum of those two things, okay, this is what we're really saying. Now, we can simplify this for this situation because we've said initially it doesn't have any of this. And at the end, when it's hitting the lake, it doesn't have any of this because its height will be 0. Everyone all right with that? So now we're back to, yeah, the initial potential equals the final kinetic. That's what we said was happening here when we first started. Okay, so that's going to mean m times g times h, initial, okay, equals 1/2 mvf. They want us to figure out how fast this thing is going when it strikes the lake. So how do I get vf by itself? Peter? Yep, divide both sides by 1/2 of m. What happens to m? It cancels, right? I got an m on the top, I got an m on the bottom. I don't have any pluses or minuses here. It cancels. Could you leave it in? Yep. You leave it in. You get the same answer we do, but it's more typing. Okay, whichever you're more comfortable with. Okay. I've often given questions like this on final exams, and once in a while I wouldn't put the mass on just because I knew in my head I didn't need it. And people freak out. Okay? Because they're like, Mr. Critter, you didn't give us enough information. I can't solve this problem. Like, okay, what do you need? I need the mass. And I'll look at it, it's a rock, and I'll say, oh, okay, it's 1 kilogram. Well, then they're plugging 1 in, like, for all of those, right? And they're happy, they walk off. And another person comes up and they say, Mr. Critter, you didn't give us the mass. Oh, it's 20 kilograms. And then they're going, okay, pretty sure he told that guy 1. Anyway, they go back, they plug that in. Another person comes up. What's the mass of the rock? 1,000. People really start to sweat, okay? Because they just don't realize the mass doesn't make any difference here, okay? All right, anyway, it's a little joke I play on people once in a while. All right, so now I've got VF squared. Do I want VF squared or just want normal VF? Normal VF, so I square root both sides. In the end, I'm going to be left with this, the square root of, okay, G times H over 1/2. Okay, I could have mgh over half of m. It's not going to make any difference. Okay. All right, so when we plug in our numbers here, we're going to have 9.81 times 30, okay, divided by 1/2, right? And that should give us 24.3 meters per second. Okay, so is there a little bit of algebra? Yep, there is. Okay, it's not terribly difficult algebra. You're either adding and subtracting or you're dividing. Okay, nothing terribly difficult. Well, you got the 1 square root, but okay, you guys can handle that. All right, I want you guys to try these two here. Okay, they're very similar to that example we just did. There's the answers. Okay, you can check them. That should be meters. Okay, give it a few minutes on those. Okay, so for the first one here, we got the 10 kilogram water balloon dropped from a height of 12 meters. Okay, so there's no other forces, so we can say that EI equals EF, okay, which means initial potential plus initial kinetic, okay, equals, okay, final potential plus final kinetic. Now, if we can, we try and eliminate any that happen to be 0. Since I'm dropping it, it doesn't have any velocity or speed initially, so there's no kinetic energy. And since it's hitting the ground at the end, it doesn't have any potential finally. Okay, so we just need to go EP equals EK. M times G times H initial equals 1/2 MVF squared. Okay, I'm looking for V, so I divide both sides by 1/2 of M. Okay, you can cancel the m's if you want. If you're not comfortable with that, you don't have to. I always do because I like saving myself work. Okay, then I square root to get rid of the square over there. Okay, so that means then that V is going to equal the square root of 9.81 times 12 divided by 1/2. Okay, and as we saw here while we were working on this, dividing by 1/2 is not the same as dividing by 2. Okay, dividing by 2 puts something in half. Dividing by 1/2 actually multiplies something by 2, right? And so when we do that, we should get 15.3 meters per second. Okay, questions on 11 there? Okay, how many people are done 12? All right. So, 30 kilogram child on the trampoline jumps vertically into the air with this initial speed, 1.60 meters per second. Okay, calculate how high the child will rise. All right, any forces other than gravity? No. Okay, we're not counting the elasticity of the trampoline because it says she just jumped off of it. It doesn't say the trampoline threw her up. Okay, so we're going to say EI equals EF. Okay, and again, we start out with all of this. I know it seems kind of silly for me to write it all, but you're going to see why I write it all every time. Okay, when we start getting to some that are a little bit more involved. Okay, so at the beginning this time, she has no potential energy because we're going to assume the height of the trampoline is 0. Okay, and that means she is moving 1.6 meters per second. And then at the end, she doesn't have any kinetic because at your maximum height, how fast are you moving? You're not. Okay, if I throw something up in the air, at its highest point is where it's turning around because as soon as it leaves my hand, it's accelerating downwards. Okay, so it's getting slower, 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 stopped, now dropping. Okay, everyone follow me on that one? Okay, so always at your maximum height, your velocity is 0. Okay, so I've got this set up now. I can go 1/2 mvi squared equals mg hf and solve for hf. So divide both sides by mg. Okay, m cancels again. Right, when I plug in my numbers here, I'm going to have that hf equals 1/2 times 1.6 squared divided by 9.81. Most common mistake I see when people are solving for height is that they start square rooting and squaring. Okay, is h squared? Then you don't have to square root anything. Okay, this has to be squared, yes. Okay, but you don't square root to solve for h. All right, so 1/2 times that, that should give us what, 0.13? 0.13 meters, which is what, like that far? It's a little kid. Okay, that would be exciting. Okay, questions on that one? All right. Now, looking at this thing here, we looked at one of these when we first started talking about energy, okay, a pulley system. What kind of energy does this have if I'm holding the heavier mass so that it can't move? Potential. Okay, it's got potential energy because both masses are above the ground. Okay, when I let it go, the 2 kilogram mass is going to move downwards, and the 1 kilogram mass is going to move upwards. Now, this is a situation where sometimes people will make the mistake of thinking that energy can be created here. Okay? When this drops, this speeds up and moves up. So it not only gains kinetic, it also gains potential. All right? Where is all of that coming from? Right. The potential energy of this. Remember, this is a system. These objects are connected. Okay? This system cannot create energy. It can't gain energy. There's no work to be done here, okay, other than the work that was done to move it to this position and give it its initial energy. All right? So when I let go of this, it's going to fall, but not all of its potential energy will be converted into its own kinetic. A lot of it will be used to do work on this part of the system. Okay? So as a result, this one loses energy, this one gains energy, but the system's total energy remains the same. Okay? This is kind of one of those weird ones, right? Where it looks like there should be more energy in the system than it started with, but there isn't. Okay? All right. So example 2.8 here. Oh, we already did that one. That was the force times distance one that we talked about a few minutes ago. Okay, we'll skip that one. All right. So these two practice problems here are very much like work energy / conservation of energy, and I've often had questions like that on a unit exam. All right, so let's have you guys try those. Okay, I'll give you a few minutes. Okay, so you're going to be looking at EK, EP, possibly some FD in there. All right, sorry, no FD in there. Okay, just EK and EP in that one. Peter. Oh, you're just stretching. Okay. All right, I'll give you a couple minutes on that one. See if you can figure those ones out, and then we'll go through them together. Okay, so let's have a look here at number 13. Very much like the 11 and 12 that we did here a few minutes ago. Okay, they're telling us the total mechanical energy of the dart is 0.481 newtons. Okay, and they're telling us the speed and mass of the dart. Okay, so mechanical energy equals EK plus EP. All right, so this is actually easier than the ones we've been doing. Okay, so we're looking now for gravitational potential energy of the dart. So I subtract EK from both sides, and that leaves me with EP. So I'll have 0.481 minus 1/2 times 0.02 times 4.1 squared. Okay, when I do that, I should get that the potential energy of the dart is 0.3129 newtons. How high is the dart? Okay, so how did we do that? Well, we said that EP equals m times g times h, so we took this number here and we divided it by m times g. Okay, so we went 0.3129 and divided it by 9.81 times 0.02. Okay, yeah, and we get 1.59 meters. Hey, that doesn't seem right somehow. That is really strange. Oh no, no, that's got to be right. Okay, I'm dividing by a decimal here. Okay, 0.3129. Okay, divided by 9.81 times 0.02. So when I'm dividing by this, I'm dividing by a decimal, which would make that top number bigger. Agreed? I like my reasoning. Okay, because that's the answer. 1.59 meters. Okay, it's not a very heavy dart. Hey, think about it. If you're throwing a dart, you're throwing it from about eye level. It's about 1.5, 1.6 meters off the ground. Right? You're not throwing it from down here. Well, if you are, you're not playing darts right. Okay, how many people have done number 14? How many people are stuck? Okay, I'll give you a couple more minutes on 14 before I do it. Okay, for number 14 here, guys, okay, what we want to do here is calculate now the speed, okay, at the bottom of the arc. Now, if you got a pendulum, this is essentially what you have. Okay, you have a mass on either a rod or a string, okay, that simply swings back and forth. All right, that's a pendulum. All right, a pendulum converts potential energy from here to kinetic energy at the bottom. All right, so at the bottom of the arc, it only has kinetic. Even though it's still above the ground, it can't fall any further because it's attached up here. Everybody with me? Okay. So we want to find the speed at the bottom of the ball, at the bottom of the arc. Okay, we're going to assume, okay, it was pulled, so it was a vertical distance of 10 centimeters up. So here's our diagram. Okay, here's the final position. Okay, here's the initial position. The height is 0.10 meters. All right, so we can say then that EI equals EF. The potential energy here is going to equal the kinetic energy there. Right, so M times G times H initial equals 1/2 mv squared. And I'm looking for, okay, VF here. So I divide both sides by half of M. Okay, M cancels, take the square root of that, and I've got V. Right, so V will equal square root of 9.81 times the height, which was 0.1 meters, okay, divided by 1/2. When we do that, we should get 1.4 meters per second. Okay, so it was a law of conservation of energy question. EI equals EF. Okay, that's what we're going to be working on tomorrow as well. Okay, we'll work on some more of this law of conservation of energy stuff. We'll be practicing that. Okay, next week we're going to do a lab on energy conversion. Okay, which starts out very much like the work lab. You stretch the rubber band, except this time you shoot something with it. A little cart that rolls along the ground. Okay, and we find out how much of the energy, the work you do, is actually converted into kinetic energy of the cart. You'd be surprised just how inefficient that conversion really is. Okay, there's a lot of energy lost in the interim.